What if you could see the future of a machine before it breaks, or simulate changes to a building without touching a single brick? That's the promise of digital twins. Today, digital twins are powering smart cities, industrial automation, energy systems, and even healthcare. But here's the thing, a digital twin is not just a 3D model or a dashboard, it's a layered system. And in this video, we are going to break down the layers of a digital twin, what they are, how they connect, and why each one matters. By the end, you'll clearly understand how raw sensor data becomes insight, prediction, and real world action. Let's dive in. What is digital twin? Before layers, let's align on the definition. A digital twin is a virtual representation of a physical asset, system, or process continuously updated using real world data. That asset could be a machine, a building, a wind turbine, a factory line, or even an entire city. What makes a digital twin powerful is continuous synchronization between the physical and digital worlds, and that synchronization happens through layers. Think of a digital twin like a human body. Sensors are the senses, data is the nervous system, intelligence is the brain, visualization is how we communicate, actions are how we move. Now let's break those layers down one by one. Layer 1, Physical layer. At the foundation, we have the physical layer. This is the real world asset. Machines, equipment, buildings, infrastructure, vehicles. This layer includes motors, valves, HVAC units, turbines, production lines. Without a physical asset, there is no digital twin. But physical assets alone are silent. To make them speak, we need sensors. Layer 2, Sensing and Data Acquisition layer. This is where the digital twin comes alive. The sensing layer captures real-world conditions using temperature sensors, pressure sensors, vibration sensors, energy meters, CO2 sensors, flow and velocity sensors. These sensors continuously generate raw telemetry data, but raw data is messy, different formats, different frequencies, noise, and errors. So this layer often includes edge devices, PLCs, gateways, embedded controllers. Their job is to filter data, normalize it, timestamp it, secure it. Now the physical world has a digital voice. Layer 3, Connectivity layer. Next comes the connectivity layer. This layer answers one critical question. How does data move from the physical world to the digital one? It includes wired and wireless networks, industrial protocols, messaging systems. Common technologies here are MQTT, OPC UA, HTTP and REST, 5G, Ethernet, LoRaWAN. This layer must be reliable, secure, low latency, scalable. If connectivity fails, the digital twin becomes blind. Think of this layer as the bridge between reality and simulation. Layer 4, Data Management layer. Now we enter the data management layer, one of the most critical and underrated layers. This is where data is stored, organized, modeled, contextualized. Key responsibilities include time series storage, asset hierarchies, metadata management, data quality checks. This layer turns raw sensor values like temperature equal to 72 into meaningful context like supply air temperature of AHU3 on floor 5 at 10:32 am. Without context, data is useless. This is also where historical data lives, which enables trend analysis and learning over time. Layer 5, Digital Model layer. Now we reach the heart of the digital twin, The digital model layer. This layer represents how the asset works. It may include physics-based models, behavioral models, rule-based logic, statistical representations. Examples: thermodynamic models for HVAC, stress models for turbines, flow models for pipelines. This is what differentiates a dashboard from a true digital twin. The model understands cause and effect, dependencies, system behavior. Change an input here and you can simulate outcomes before they happen. Layer 6: Analytics and Intelligence Layer. Now let's make the twin smart. The analytics and intelligence layer applies algorithms, machine learning, AI models, anomaly detection, predictive analytics. This layer answers questions like: is something about to fail? Is performance degrading? Can we optimize energy usage? What happens if we change this parameter? Instead of reacting to problems, you can predict and prevent them. This is where digital twins deliver real business value. Layer 7: Visualization and Interaction Layer. A digital twin is useless if humans can't interact with it. The visualization layer includes dashboards, 3D models, digital maps, AR and VR interfaces. This is where users monitor systems, explore simulations, investigate anomalies, make decisions. Good visualization turns complexity into clarity. It's the difference between drowning in data and understanding what's happening. Layer 8: Action and Control Layer. The final layer closes the loop. The action and control layer sends decisions back to the physical world. This could mean adjusting set points, triggering maintenance, optimizing schedules, automatically controlling equipment. At this point, the digital twin is no longer passive. It becomes an active participant in the system. When these layers work together, you get visibility, prediction, optimization, and ultimately better decisions.